Welcome to the afternoon section. Yeah. And Anton Svetlichny will introduce the next speaker. So please, Anton.
Thank you very much, Andrei. So, right now I'm happy to present the new lecturer, Professor Paul Griffin. Paul was born and grew up in Ireland, where he finished his undergraduate degree in applied physics from the University of Limerick. After that, he finished his PhD in atomic and quantum physics from Durham University in the United Kingdom and did his postdoc at Georgia Institute of Technology. From 2010 to 2011, he was a guest researcher at the National Institute of Standards and Technology in Gaithersburg. And in 2015, he started as a lecturer in Starkly. But right now, currently, he is a full professor and the Rosenberg Chair in Quantum Sensing, whilst leading research in quarks, magnetometry, and atom interferometry. And today, Paul is going to give the lecture about the quantum magnetometry. So, Paul, I'm happy to give you the floor.
Perfect. Thank you, Anton. Hopefully you can see slides okay.
Yes.
So I'm going to talk about, yes, exactly, atomic magnetometry. So there's a little bit of physics, a lot of engineering in this part here. So I didn't get to see too many of the talks earlier. And by the way, apologies that you're getting another accent. So as Anton mentioned, I'm from Ireland, and I will try and speak more slowly and clearly than I would with my dad, for example. But my background, which is described there, skipping on to this one, is working. The group I'm in is called the Experimental Quantum Optics and Photonics Group. So if you've never heard of the University of Strathclyde, which most people haven't, we are a technical university based in the city of Glasgow. So you look at the road maps of Europe and you find the bit where the roads stop, which I can tell you is where the good bits of the countryside start. We're based in the city of Glasgow, and we are historically a technical university, which means lots of engineers. So there's a number of academics who work in different fields of quantum. It's almost like a Marvel movie. We stick quantum in front of anything and think it's good as a result of that. We're working in different areas of atom interferometry, which you'll have seen some talks about, atomic clocks, which Alex mentioned in the last talk, and this idea of microfabricated platforms. And that's one of the things that drives my research is research in the lab is really good. Can we think of ways of getting it out of the lab? And I like this match between fundamental physics and kind of applied research as well. So that brings into this quantum tech at Strathclyde, what we're trying to do. So a lot of my work and our group's work are based around these ideas of developing platforms. Can we make a system, which Alex described, so we've worked with them for some years on developing this idea of a cold atom platform. If cold atoms are good, why can't I just buy them off the shelf? Another aspect we look at are these things called MEMS components for quantum memories, for magnetometry, for clocks in various areas. Wouldn't it be really good if I could just go to a company and buy that subsystem? And that's what we're trying to work on. So we've done lots of different works in these areas, and today I'm going to focus on this optically pumped magnetometry because I think it's an example of one, the hype of quantum technology is really using old physics, and what we're using are some modern adaptations to move forward. Most of the physics of atomic magnetometers, quantum magnetometers, are from the 1950s, pre-lasers. The other thing is that I think a big thing about quantum technology is that it's quantum technology. It is not quantum physics. And some people get really quite, I'm going to say, annoyed because that we're not using entanglement, we're not using some real higher order coherences. What I'm going to say in quantum technology, and given the talks you've seen, is that it's using quantum systems and quantum-enabled systems that allow us to do something better than we could beforehand. And if that something is that we can make things smaller and cheaper, I'm not going to get into too much detail about whether it's important that we have entanglement in the system. It's we can do something that we couldn't do before, and it's branding, unfortunately. What I'm going to focus on in this period is talking about measurements of magnetic field. So there's lots of different types of magnetic fields we could think about. There are going to be Earth's magnetic field, which varies on, it's not just a constant. The North Pole is somewhere just about Canada at the moment. It varies around the Earth, and we come to this unit and say it's roughly half a Gauss. It's about 50 microtesla, but there are regions, particularly in the southern Atlantic anomaly, where it drops down quite a lot. An interesting magnetic field that we all hopefully care about are the magnetic fields coming from the human heart. When your heart beats, it is due to currents flowing through action potentials that cause the muscles to contract in the correct order, and you get these very kind of characteristics seen from TV, what these kind of love-dub profiles. When your brain fires and your neurons are trying to think about some interesting quantum mechanics, the currents are flowing through the neurons, and those currents generate magnetic fields. Can we measure those kind of fields? And some things in fundamental physics, in very much anti-fundamental physics, in things like archaeology. If you heat up rocks in a magnetic field, those rocks become very slightly magnetic. And by moving magnetometers over the surface, can we do things like measure without having to dig what is going on underneath the ground? And this is an example of a Neolithic ditch. Underneath the ground, below the surface, you can map out the magnetic signatures. I'm going to come back to this later, but also the thing is that magnetic fields vary very quickly in position. So this is an island called the Isle of Mull off the west coast of Scotland. You get a lot of really beautiful islands. And this particular island has, it is known you should not use your compass if you're hiking in this island. And the reason being is that this is a map of the magnetic anomaly, where the scale we're talking about here is on the scale of microtesla per kilometer. And remember, the Earth's magnetic field is 50 microtesla. So by walking 1 kilometer, the magnetic field around you is changing in the order of 2%, which means your compass is going to swing around. So on a misty, cold day like we get, where your distance, your vision is going to be affected by the weather, it becomes complicated trying to orienteer using maps to navigate, unless you are aware of the fact that you shouldn't do it. And I'm going to come back onto that afterwards. And if you ever get a chance to come to Scotland, the Isle of Mull is an extremely wonderful place. And there's also variations in time due to things like the Earth's magnetic field that we measure changes due to solar storms, but also changes due to the time of day, because as the sun rises, the ionosphere above us gets charged, and we can see these diurnal, on a case of a day, these low frequency changes in the magnetic field as the bright UV sunlight charges up the atmosphere above us. And things like the aurora, and we're seeing changes here again that are in the order of roughly 1% of the Earth's magnetic field. This creates a lot of problems, but it also creates a lot of interest as far as I'm concerned. So here's a cartoon kind of picture of the ranges of interest of magnetic fields. So we use it like a lot of physical units. This SI unit is a Tesla, and it's either extremely big or extremely small. In this case, it's too big. A field of a Tesla is the kind of field that is going to be used in scrapyards to pick up cars. A fridge magnet at the surface is a field of about 5 millitesla. 5 millitesla is the level that if you have a pacemaker, it becomes an issue. It starts actually affecting the way that these artificial pacemakers work. But the Earth's magnetic field, what we would call the geophysical field, is about 50 microtesla, or half a Gauss, if you use those kind of units. All around us, the fact that we're just using electric power, the noise from the magnetic field, 50 hertz fields that we experience, are on the scale of about 1% of the Earth's magnetic field. So the fact that you plug in your laptop, you start generating noise because you're drawing current and using the right-hand rule. And the fact we use AC current means that we're going to get changing magnetic fields over time. And then we can go down to the fields from your heart, is about 10 picotesla. And then again, about another 2 orders of magnitude below that is the field at the surface of your head from your brain firing. So this is a field generated by thousands of neurons, so clumps of neurons firing within the human head. So this creates an interesting problem that there's lots of range in here, what we're going to call dynamic range. It's very hard to make one sensor that works in a huge range. But the range I'm going to kind of focus on is this very low range, 1 femtotesla to 1 picotesla. These are millions and billions of the Earth's magnetic field. Can we measure these kind of fields in addition to actually being in the presence of this Earth's magnetic field? So in the presence of a 50 microtesla field, 5 times 10 to the minus 5, can I measure these changes about 1 part per billion in the field around us? And of course, the answer is yes, otherwise I wouldn't be talking. So what is the state of the art? I'm going to use 2 axes here, which is sensitivity. It doesn't have units because it just it gets complicated. And then on this side here, we're going to use this term called SWAP, which you'll hopefully have come across, which is size, weight, and power. And typically there's a C at the end of that for cost as well. So the kind of sensors you have in your phone, which are used for a compass, they're going to use what's called a Hall effect, which is a very cool feature, but let's not get into it. These are small, cheap, and not very good, but they're good enough to tell you which way is north and which way is east and west. Scaling up, you've got devices called flux gates. Flux gates are using the magnetic response of particular metals. And if you apply and you measure a hysteresis curve, the presence of an external field changes the hysteresis curve. These are getting much more sensitive. This is the workhorse of sensitive magnetometry and used, for example, in this case here, like geophysics, mine sweeping, and so on. And the state-of-the-art is a thing called a SQUID, which is a superconducting quantum interference device. It uses rings of superconductor at ultra-low temperatures, and then uses the fact that changes in the magnetic field through that generate Josephson kind of effects. And what we would like is to get the performance of a SQUID, which uses superfluid helium, and generate a device that is lower cost, more importantly, but also if we can get away of the fact of having to use cryogenics. And the devices we use are battery powered. Same battery we use a 5-volt battery, the kind of thing you'd use to charge your mobile phone. And it uses atomic physics. So why would we like to use atoms? Fundamentally, it's the fact that they're inherently identical. If I do an experiment on for example, lithium atom here in Glasgow, and you do one in Ukraine, and someone else on the other side of the moon does one, we're all going to get the same result in these measurements. We're going to measure the same energy levels. And those energy levels are the interesting point. Quantum and atomic physics is very, very well understood. We're not doing anything new. But the thing is that theory and experiment match extremely well. So any deviation from the theory has to be due to some external perturbation. If I engineer my experiment well, that means that perturbation is something I want to measure rather than some unwanted signal. This control from lasers means that atoms, and particularly I'm going to look here at the alkali atoms on the left-hand side of the periodic table, they have got one electron, and the scale of energy for making those electrons jump between different levels is in the visible or near infrared, in the ideal situation for laser beams. So the lasers we use, or the devices we use, are just laser fields, which give us this really exquisite control over the internal state of the atom. And from that, we get these ultra-precise measurements that we can then make. So a hand-wavy idea we're going to think about is that I have a glass cell. This glass cell is something you can buy commercial off the shelf for a few €100. Inside there are the gas of atoms. I'm going to think about just using cesium for sake of argument, but it could be any of the alkalis. The density is very low, 10 to the 9 atoms per cubic centimeter. So it's going to be 10 to the 15 atoms per cubic meter. So it's a dilute gas. And what we do and what we think about inside this system is that this atom of cesium has one valence electron on the outside. All the other shells inside the atom are closed, which means all the electrons are paired up, so we can neglect the effect of those to first order. But that one remaining atom, as it spins around, creates a magnetic field. Again, we know the atom doesn't move like a ball around, but that picture works as the electron moves in a direction, it generates a current, and that current creates a magnetic field. And so each of these individual cesium atoms behaves as if even that it's a little bar magnet with north and south facing poles. And of course, the reality, these are magnetic dipoles inside the atom. And so how do I manipulate the magnetic dipoles? I do that by shining on a laser beam. And that laser beam, if I have some angular momentum in the laser beam, what we're going to call polarization, that angular momentum is going to allow me to impart angular momentum onto the atoms. What it means is I can take those atoms and point them all so they're in the same direction. And what I'm describing here is very much a mechanical picture, right? It's going to hold when we get into more detail, but this mechanical picture I think is very useful because, like all good toy models, it lets us get into the physics quickly and then we can find out more details later. Once those atoms are pointing in one direction, what do we need to do? Well, if I have a magnetic field that is pointing any direction other than along the same direction as the laser, but if it's pointing in some other direction, what we get generated is a torque in the system. So the magnetic field is pointing in a direction, the spins are pointing in another direction. We look at the cross product of those, and it ends up what we're dealing with precession. These magnetic spins will precess around. And the nature of the precession then can be read out. So if I come in with a weak laser beam, so the first time I came in with a strong laser beam, shown here as being bright orange, and then I come in with my weak laser beam, I can do a very, it's not a non-destructive measurement, but it's a minimally destructive measurement on these atoms. And I can read out by measuring the absorption or measuring the state of change of polarization of the laser beam or something else, the precession frequency of these atoms. So the gist of what we're trying to do is that I've got this random orientation. It's a gas, it's in thermal equilibrium. They point in whatever direction you want to point. I make a non-equilibrium distribution by shining a laser beam onto the system with controllable parameters. And then the atoms start to oscillate at a frequency which is directly proportional to B. This proportionality constant is called the gyromagnetic ratio, and it is fundamentally given just by quantum, right? It's just the nature of the atom. It's nothing to do with the light I've shone onto it. It's nothing to do with anything else. All those atoms of cesium anywhere in the universe are going to precess at the same gyromagnetic ratio. And this precession frequency, I'm going to use units of microtesla, but in the Earth's magnetic field, we're talking about roughly 100, 200 kilohertz oscillation frequencies. And these are very nice frequencies that one can measure with very simple electronics. And so this is the power. What we're trying to do is I will measure the oscillation frequency of these atoms by doing a weak measurement on the atoms themselves. And from that, I get a direct measurement of the magnetic fields. The more accurately, the more precisely I can measure the oscillation frequency, the more accurately and precisely I can measure the field around me. And if I can do this quickly enough, which we're going to call bandwidth, I can measure high frequency. I can measure perturbations in the system over time. And this is what the majority of what I'm going to talk about is about. This is really neat physics. This is what the Nobel Prize for Alfred won for, is that the interactions that are happening are within the ground state. I describe this as being magnetic dipoles that are spinning around. The reality is, if we think about some structure of the atom, there's some Zeeman states included in this. I'll come over this again very briefly. But we're getting these magnetic interactions, which are typically in this radio frequency regime, which it's even pointless to consider the concept of for detection. There's no way of detecting individual photons at this kind of frequency. But what we do instead is use optical interrogation. So if I've got these two transitions in cesium that are separated by, in this case, hundreds of nanometers in the optical regime, I can measure the effects in the radio frequency regime by the amount of light that's absorbed or some other perturbation on the light. So what does that look like? What we have in our system that we're going to come on to is we have a chip scale laser. This is what's called a VCSEL. These are about 100 microns cubed. We have some very simple optics, which is going to generate a collimated laser beam. We have some polarization control. We have a very small laser vapor cell for spectroscopy. And then we have some way of measuring here. We're measuring the change of polarization. Basically, the electric field of the laser, as it goes through the atoms, does it get perturbed to the side? And the transformation that has come about in quantum magnetometry, in this particular case, optically pumped magnetometry, all these work was known about before lasers came around. But what has happened in transformation is that, first of all, lasers were invented. Then secondly, small lasers were invented. And then thirdly, the patent on those small lasers ran out, so I can get them cheaply. The next part that changed is on the electronic side. Digital electronics, kind of things like field programmable gate arrays, but low-cost Arduinos even have really just transformed the way that we can do signal detection and signal analysis really carefully. That improves my sensitivity, improves my scale, how small I can make these things, and improves the availability of components. And ultimately, what we're trying to do is we have a resonance system. These atoms want to oscillate at a particular frequency, and my job now is to nail down that frequency, to measure as accurately as I can. If we start looking at what's happening inside the cesium atom has got a much more complicated energy structure. So the hyperfine quantum, the spin quantum numbers of cesium in the ground state are F equals 3 and F equals 4. Each of these has a degeneracy of 2 times that spin number plus 1. So this F equals 4 has got 9 sublevels, Zeeman sublevels within it. The F equals 3 has 7. We also have these excited state transitions that we're probing. So if I want to do the full Hamiltonian of the system, I need to go off and figure out how to do this 32-level Hamiltonian or learn how to use Python. So we transfer angular momentum by this laser beam. I use this notation of sigma plus to describe the magnitude of the angular momentum that's been transferred into it. We use these MF, these Zeeman states, this magnetic quantum number. We look at the Clebsch-Gordons, these dipole matrix elements between the different individual states. And by doing appropriately polarized laser beam, we can generate what's called spin orientation or spin alignment. What spin orientation is, we create this system which at room temperature should have an equal distribution amongst all these 16 levels. But by the presence of a laser, I can put all the population into one of these states. If you want to think about this as temperature, we can reduce temperature very, very, very low. And then we measure the evolution. This is going to be a Liouville equation. We have this field interaction. We have this relaxation term. It's just due to the fact these atoms are still moving around at 200 meters per second. These are 300 Kelvin atoms. We are not using laser cooling like some of the other talks you'll have seen. And the fact of repopulation, my laser beam, even when I said it's a very weak measurement, it does something interesting to the system. And then depending on how I probe or how I prepare my laser, my interaction Hamiltonian is going to have these coupling terms, these off-diagonal terms, Rabi frequencies, which is saying that I'm going to put my population either into one of these stretch states like so, or I'm going to put it into a distribution of states. So it's going to be in one end and the other. It's going to look like by one end and another end means that I'm going to get my spin is an average going to be 0 of the whole system, but I'm going to get roughly equal population in the stretch states, plus MF minus MF. You can also consider this as a bunch of multipole moments. You can think about this as spherical harmonics, where I'm going to have this electron distribution inside my system. And as I start applying these changes in the internal structure, the internal population of the states, I start thinking about dipole and quadrupole moments of the system. As the laser beams go through, this allows us to measure these kind of rotations of the system, and ultimately comes back in that we're going to measure the interaction of the atom with the magnetic field, and then I can measure the interaction of the laser beam with the atom, and hence measure the magnetic field. There's a lot of physics in the background. This physics was done by very, very smart people about 70 years ago, and the nice feature is now that we can go and do stuff with it. So what are the kind of applications? And that's what I'm going to focus on from here pretty much, is that there are two orientations, or two different ways you can work in these systems. So when we started working in this field about 15 years ago, there was two big pushes, which is, will I take my magnetometer and put it in a shielded environment, get rid of all the noise around it, and really push down to the absolute limit of what we can measure? Or will I take a magnetometer and use it outside literally in the field? Will I make a magnetometer that I can take around and in the presence of noise measure very accurately? And the real push at the time was in these shielded magnetometers for lots of reasons. One, it's just cool, right? You can measure down onto single flux quanta of magnetic fields. But in healthcare, there's this real part here which you can start measuring, really go to measure the magnetic field from the brain. And this opens lots of opportunities. There's a very particular problem about epilepsy and diagnosis of epilepsy. And the problem comes about due to the fact that humans are salty, right? We're conductive. So when you try and measure electrical signals on the surface of the body, the human looks very much like a Gaussian shield. So if there is a magnetic field source inside my head, or an electric field source, when I measure the electric field on the surface of my head, the field has been it becomes blurred, it becomes distributed over the surface, and localizing the position of that source becomes a very complicated technique. However, we're transparent to magnetic fields, and so the magnetic source doesn't go through the same effect. The magnetic conductivity is non-relevant to that point. And so that allows you to measure more precisely the location of the effects. And for something where you have to do brain surgery afterwards, it's quite important you know where to stick that scalpel at that point. And this is a big push, and I'm going to tell you that it works very nicely. The push we've been looking at in unshielded is whole things like security. Can you do GPS denied navigation? Can you start measuring unexploded ordnance? Can you measure mines? Can you detect drones at a distance? In geophysical field is surveying. Can you just basically measuring the ground and the earth around us for mining and other applications? And in materials, start measuring nuclear magnetic resonance. Can we do chemical species measurement in Earth's magnetic field? Can we do things like conductivity maps, detect defects in systems? I think there's some questions asked beforehand, particularly in Alex's questions about the scale of our system. So this is a picture from one of my other labs. This is the atom interferometry experiment. We are not like Mike Linsky, you saw yesterday, talking about bringing these into we're working still in the lab doing Sagnac measurements. We've got an optics table that is a ton of steel. It's 3 meters by 1.5 meters. We've got a lot of stuff in here, including PhD students. We've got cables everywhere. This is not an experiment that will ever be, and to very clear, it's not something that's ever going to go outside of the lab. And this has been one of the pushes, as I said at the start, is I think a good physics experiment is one that you can, depending on your level, but for mine, I'm trying to say I can measure interesting features. I should try and measure those interesting features. And so our progress has been from the lab, where we did set up things in optical tables using lasers, to making things where we started getting still components. If you recognize these, if any of you work in a lab, this is just using Thorlabs components that we bolted together. Basically the same stuff that's on the table, but we tried to make it not on the table. Down towards where we started making our own printed circuit boards and pulling together the lasers, we bolt everything together, towards our devices now, where the full magnetometer is included in this component here, which is about 3 centimeters cubed. The cables that are coming in and out are for applying signals and for controls and for measuring the signals as well afterwards. And I'll go through what's inside that, as I said beforehand. We have these chip scale lasers. We've got some commercial off-the-shelf optics, and we have these little vapor cells, which is actually one of the more complicated things in the system and in the electronics. The lasers are, as I'll get onto, these are very similar to what's used in LiDAR. So cesium, by chance, has the wavelength that is used for that is very similar to what is used in car LiDAR. So any system in autonomous vehicles are using on order of 10 to 25 LiDAR systems, just so they can know the navigation around them. So these are huge manufacturers on a scale of billions per year. And so they work for what we need to do. The lasers we use are a device called a VCSEL. So this is a very low power laser. And the interaction of the atom-light interaction in cesium and all the alkalis is actually very strong. So we do not need high laser power. These vapor cells are manufactured in I'll come on to that very briefly, but these are something we make in-house because that was something that you really want to make sure the environment is very well understood. Inside that cell is cesium, and the cesium is not being perturbed by something else. And we have a whole bunch of analog electronics and digital electronics. So the analog electronics are for driving the system. I want to apply current to this laser, and I want to make sure that there's very low noise. And for that, you really have to use old school resistor capacitor kind of systems. We apply some control system to these lasers, and we measure the polarimeter, and then we do the detection using digital electronics, field programmable gate arrays. And that's these components of lasers, cells, and polarimetry. And we come down to the size of the system. These numbers are right old. We've gotten a lot smaller than this one. The whole device is 10 cubic centimeters. It is 50 grams in weight. And I added this on because I know there were some questions beforehand about how small can these things be made? Can they be put on drones? Yes, we do, frequently. And 5 watts of power, most of that is used in the digital control system afterwards, and that can be made much smaller. Very briefly, I'm going to mention these vapor cells because the origin of this came from these chip-scale atomic clocks. So about 20 years ago, a huge amount of work was put in by the US onto trying to figure out, could you make a clock that was about the size of a grain of rice that would have atomic performance? By atomic performance means that it wouldn't drift over time. When it said the frequency or if the frequency of this energy level was 9.2 ... gigahertz, it measured the exact same frequency all time. It may not be the most precise measurement, but it's very, very accurate. And so this is a work that was done at the National Institute of Standards and Technology, where you've got these lasers that I talked about, and everything pulled together is the size of a grain of rice and uses about 200 milliwatts of power. And one of the things that were included in that are these vapor cells. So these are using glass silicon methods, because this can be made on scale using standard clean room technology. Cesium is added, or rubidium, whatever element you want to use. I keep saying cesium, that's just the one we use. And cesium is created or is formed inside the system, and then the whole system is sealed together using this technique called anodic bonding. Why is that really important? One is that the traditional way of making vapor cells is an art. It is people glass blowing who have molten glass. They blow through tubes and they cause these beautiful shapes to form. That is very good if you want to make very customized equipment, and this is still what's used in chemistry and physics labs around the world, or in art. But what I'm trying to say, if I want to make thousands of these, we need to get away from that kind of system. And that's one of the pushes that we have on. So these are kind of pictures I'm taking of how the cells that we use beforehand are made. It is using flames and glass and pulling, and it really is an artistry, which unfortunately not many people know how to do anymore. So in the microfabrication side, we make these cells ourselves. They're done on a commercial scale. We can make cesium, rubidium, potassium, take your pick. And the point I'm making here is that the optimized gas content inside those cells is rubidium and only rubidium, or cesium and only cesium. So the chemistry is very well controlled. If I want to, I can put in lots of other gases, and we typically do include what's called a buffer gas. The buffer gas is important because these atoms are moving. You look at the kinetic energy of the system, they move about 200 meters per second, which means that the atom very quickly collides with a wall, and that would be a non-spin preserving. It would be a very naive way of saying it would be incoherent. Basically, it screws up the system very badly. What we introduced in as a gas, typically nitrogen, which has got no outer electrons. And so if I put about an atmosphere of nitrogen inside that system, that cesium atom is just going to bounce around between the nitrogen atoms, and will take of order of tens of milliseconds before it collides with the wall and has an incoherent interaction. And the nitrogen has no deleterious, there's no bad effect on the spectroscopy, but we need to be able to control that gas content. And these chip scale lasers, these are made on the scales of thousands for these wafer scale fabrication. And that would be means, again, we're trying to make a product, not a product, that's not my role. We're trying to make this device in a way that if it's very good, you can start thinking about making many of them. And I'll try and motivate that afterwards. The other feature that came into is that these first two parts were not available to Alfred and people in the 1950s when they were first doing these magnetometry experiments. The other component was not available was embedded processing, and this has completely changed. Arduinos have just completely changed the way that we can work. We're using a technique called homodyne detection. Ultimately, what we're doing is that we're making the system oscillate, and I'm trying to measure that oscillation frequency as well as I can. And so we're using analog to digital converters that have high bit resolution, so we get extremely precise measurements. And this idea of low latency feedback is using digital electronics. When I put the data in, it processes through the same speed. It goes at a particular clock frequency. So it's not like a computer where if you start doing an update, or my laptop, if I start updating my process or updating some software, the whole system slows down. Digital electronics does not work like that. It just data in, clock, 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 gets through. And so that opens, what I'm saying about new applications, is there's different modalities that we can run the laser system on, and it really changes the way that our system works, and also allows us to do new system types, where I can do very accurate measurements, very precise measurements, and I can start making distinction between whether I want to do those. The real difference it makes is in the speed of the system. If I want to make a fast measurement, for example, to detect drones at a distance, I can run the sensor in a different modality than if I want to make a very precise measurement, and that allows us to change around in those areas. So this is the big picture of what we're going to do. I'll skip over these, and I'm very happy to make all the slides available afterwards, but we have our own FPGA digital control system where we've got a CPU on board. We upload our own control systems onto it. It runs Linux. We have these things that we need to control, which is the current, the laser current, the temperature of the laser as well, because that will affect the wavelength that's been emitted. The way we heat our vapor cell up, we need to get the cell hot in order to get a high density of vapor inside, and hot means about 80 degrees centigrade. And we've got these analog front end. We need to measure the signals very well. There's a whole bunch of points that kick in here. The end result is that we can control our system, but with a system on a chip kind of device. And that works very, very well. So how does it come together? These are just some data. These are not the best performing systems that we have, but we can measure 10 picotesla. These are 3 different devices that we're looking at, or 2 different devices, sorry, and the difference between the 2 of them allows us to measure with this bandwidth of about 1 kilohertz. So we can identify frequencies all the way from 10 millihertz, or 100 millihertz, sorry, here, up to about 1 kilohertz. We can see peaks in here. This is just due to the AC noise that comes from the fact we're using electricity. So this is the 50 hertz noise that's always present. Depending on the modality we use, we can pull this noise floor down by 2 orders of magnitude. So we can measure about 100 femtotesla if we need to for medical applications, while still maintaining this high bandwidth. So kind of field trials, which is what I'll spend most of the rest of the time talking about, is that we do take these devices into the field. So Ross Prairie, Strathclyde, if you're in Scotland, it's got lots of lakes. We've got a facility out near this lake called Loch Lomond. And these are the pictures that we're taking. Scotland is wet and boggy. And so this is Ian, one of our colleagues, who's taken this control system we have here. This is the electronics and the digital system, and our 2-channel sensor. This is a classical sensor that fluctuates, and we're just logging data and seeing how this behaves over time. One of the other areas that we use this quite a lot for is going to be in, where we're really pushing towards, is measuring at the Earth's crustal field. So this is a picture taken from, it's called GeoMag, which is measuring the Earth's field. And so these are pictures. This is a map of the UK, which shows, these are the Ordnance Survey. If you're a hiker and you want to buy a map, these are the individual squares you normally would buy. However, if you look at the magnetic field anomaly, so ignoring the Earth's magnetic field, again, it's 50 microtesla. If you subtract it off, these are the perturbations from the field around. So if you're not familiar with the map of the UK, this is roughly the outline on here. So England, I hate to tell you, is extremely boring magnetically, but Scotland is very interesting. And that's just because of the tectonics of the system over time. If you look at these fault lines, then you'll start actually recognizing the geography of the system as well. Why is this interesting? Well, one, is just interesting for geophysics. If you're interested in mining oil and gas, you might care about these kind of things. But one of the things we're looking for is the fact that GNSS, the GPS signals and all the rest are vulnerable to disruption and outage. And in the current world, we're not entirely sure that the US will continue to let us use GPS all the time. So there's a vulnerability here, which may or may not happen. But if you are if you're worried about control of your systems, control of your movements, you really need to be worried about this kind of area. And so going back to, I think Alex talked about dead reckoning, is if I know exactly where I am on one of these maps, so this is a lower resolution map of Scotland, if I can measure, if I have a map that's very precise and I know where I am and I know the magnetic field, as I move along, and so this is a picture here taken, this is using the geophysical map, and these are data that we took with one of our sensors in a backpack, we can map the magnetic field as we move. So if I'm moving at a constant velocity and I measure my change in magnetic field, I can localize where I am being positioned over time. And this is really interesting because the Earth's magnetic field, it's permanent, it's fixed. So the Earth's magnetic field is not changing over time. So the environment around us does. So we use what's called common mode rejection. We use two sensors, one to measure the field and one to measure the environment around us. If you wanted to spoof this data, you'd need to create an extremely large magnetic field. And why I'm saying extremely large is because the magnetic dipoles, this scales off as 1 over the distance to be cubed. So in order to jam the Earth's magnetic field, you basically need a power station to power the electromagnet that is going to generate that. So, and this requires some clever digital processing to understand these kind of systems, but these kind of map matching techniques are used all the time, these Bayesian inference of position. Not for this particular application, but this is work that we're trying to do right now. And so the idea essentially is if I have this magnetic field map around us, I take my first measurement, I take a second measurement, a third measurement. Very quickly, I can track my trajectory through that field. So this is a big area that we're getting onto, that it's passive. I mean, you don't have to broadcast. It's not like radar where you can be detected. It's got applications in a whole bunch of range. It's not dependent on weather, not light levels. Very difficult to jam. It is by no means as good as GPS, but it's an alternative source. And it's when you're thinking about that we may need to know where we are and we're moving, it's something that is of very huge interest at the moment. On the cardiac level, this is an idea of what I was looking at beforehand. This is a model of your heart is going to be. You've got these particular fibers that current flows through, or action potentials. And as the current flows through, you get this spatial magnetic field about the heart. So this is one of the people who was first interested in it. He's got a dog beside him, and the dog's there because this guy did not do the experiments on himself. So what they have in here is that the dog called Jimmy, which is and Jimmy put his paws into salty water, and he measured the current, the biophysical currents that are being generated by the animal, and he could measure changes that correlated with the heartbeat of the dog. These were the very first measurements that were done. I like these measurements in particular because that dog doesn't look too happy at the point, but you can see him when he's standing beside his master, he's also not particularly happy. Why is this useful? It's very useful because the alternative is an EEG, requires sticking electrodes on. And as I mentioned beforehand, because the human is conductive, the electric field measurement depends on things like, are you hot or cold? Are you fat or skinny? It depends on whether, if you've got chest hair that needs to be shaved off before this measurement can be done, it's a conductive measurement. However, the magnetic signature is done at a distance. It's non-contact. It's done by holding, in this situation here, by holding a magnetic sensor slightly off the surface. You can measure the change in, these are measurements of the magnetic field generated in the left and right ventricle as a function of time going through. And so you can see that the field, as the current goes through, the magnetic field changes associated with it. And these are measurements that we took with one of our sensors. This is a prototype sensor where we measure these kind of features, these defibrillation techniques. Doing experiments in human is complicated because of ethics reasons. So we did most of our measurements actually on farm cows. And this just, the example I'm showing in here was the idea is that doing measurements in agriculture is extremely difficult because it is extremely noisy, it's extremely cold, it is extremely smelly, and the experiment worked. We could measure the magnetic field of a cow. And the idea in that one is for animal healthcare and for lots of other reasons. It's a real interest that in this magnetocardiography is because it's non-contact. It could be done extremely low cost as well. But these are things that lots of people are working on, and the applications I think are extremely interesting. The next aspect people are looking at is, and I mentioned before, could you start measuring the human brain? And this is a work that we're doing, or more importantly, our collaborators are doing, and we're sometimes involved. So what's been replaced are these ideas of superconducting quantum interference devices. So these require superfluid helium, typically helium-3, so it's extremely expensive to run. Because this is a device where these sensors are in particular positions, it's a one-size-fits-all. So if you have someone who is a child, for example, their head has to fit inside the adult-sized device. And their head clearly is smaller, so you've got a larger standoff. These measurements take about 20 minutes, and if you move more than 5 millimeters in those 20 minutes, the data are not of any use. And this creates a huge problem. But the idea of using these atomic sensors is that the atomic sensors now are attached to the head, so you can move your head around as much as you want, and you can measure and localize magnetic fields sources within the human brain. And this work is exploding across the world at this point. It works at room temperature. It does not need cryogenics. It's got a high bandwidth. It's got a high sensitivity. It's got background cancellation. There's a whole bunch of areas that are getting into it, including things like you could do magnetoencephalography on babies within the womb and other applications across the board. So these are some measurements using our prototype sensor. And we do this very simple thing where we ask someone to open their eyes and close their eyes. And we're comparing If we look at the region here where we're seeing in this particular band, which is called the beta band, where you can see there's lots of noise sources on here, but we're getting statistically significant difference at this frequency, about 8 hertz. And so the human brain is generating signals at all time. So when we tell someone to close their eyes, the noise level goes up, which is kind of strange. And reality is that the brain becomes quieter when it's processing data, which you can kind of imagine like an amplifier that's idling. It just generates noise, but when you get an amplifier to amplify a signal, the signals go down. But in this region here, when the eyes are closed, you get this large spike from these visual cortex parts of the brain. And this is the comparison that we're seeing with the state-of-the-art commercial devices that run in a similar kind of way. I'm going to skip over some of these applications because at some point what we're trying to say is that if there's a situation where you can measure a magnetic field, why not measure it to do something useful? So vehicle batteries, if you charge up a battery, why did it discharge? It discharges because there's small leakage currents within the system. The way these are measured at the moment commercially is that the battery is charged up. It is put into a hot room being about 50 degrees centigrade for a month, and then it's taken back out again. The room is hot in order to increase the diffusivity of the system. These electrons are more mobile at higher temperatures. And then you check, is there the same amount of voltage on the battery as when you put it in? And if the answer is not conclusive, you put it back in for another month. And so 1/3 of the energy in creating these large batteries is in the testing of them afterwards. But however, we have a project with a number of collaborators where we can actually measure these small changes in the current as it flows through these leakage currents. And that would allow you to do not just in manufacturing, but also in real time. You could put these into automotive, for example, in cars, but also put it onto planes where using electric batteries rather than fuel. I'm aware I'm doing a whistle stop idea on this one, but I'm trying to get the idea across here of their applications are not just for lab-based systems. There's a lot of interesting techniques that we can use. The next area we're working on is on space weather. So in space weather, this is the pictures of the aurora that we have taken off the web. These are not my photographs. But the idea in that one is that the space weather is giving us information about the magnetosphere, about the atmosphere above us. And that's interesting for lots of reasons. But a very simple reason coming in is that changes in the currents in the atmosphere affect our telecoms and power systems. So if you think about any particular country that has a national grid, if there's power flowing through the grid, you at some point have a loop, a conductive loop. And so if there's changes in the magnetic field, that generates a secondary current within that loop. And that secondary current within the loop corresponds to heat and loss in the system. And if there's a magnetic storm coming in, for example, that's a rapid change in magnetic field, and a large change in magnetic field corresponds to a larger induced current. So we need to be able to predict space weather, because if there is a solar storm, that can cause catastrophic damage to grid and telecommunication systems. There's an event called the Carrington event, which is the late 1800s, which physically caused systems to explode in the grids at that time. And the advantage was that there wasn't a huge amount of national grids in the 1880s. But if that happened at this point here, the important thing would be able to predict it's going to happen, controllably switch off the system and turn it back on again afterwards. So the project that we have is developing this array of sites across the UK and Ireland where you can give better measurements. And so we have installed our sensors in these different islands here off the west coast of Scotland, where there's currently gaps. And this is the idea to measure better the model of the Earth better. So this is Marcin Rozowski, one of our PhD students, on a typical cold day where we're measuring signal to noise ratios of 90 dB, sorry. So this is a part per billion measurement in the Earth's magnetic field. We've got a solar panel. Solar panel does not work very well when you're 55 degrees north, but this system is here in a field. This is a sheep field, so we put a fence around it. And I'm emphasizing this just to emphasize we've gone far, far away from air-conditioned labs at this point. And we leave the system, it broadcasts the data to us, low frequency, but we get one measurement per second. And the system turned off in December when the winter in Scotland kicked in, and it's turned back on again, and it just works by itself. Some of you, if you recognize the name of Islay, may know that that part of the world is much more famous for its Scotch whiskey. So if you like smoky, peaty whiskies, this maybe is part of the reason why Marcin is so happy in these pictures. One last example I'm going to give in this area is on magnetomyography. So when nerves fire in the arm, if you move your fingers are moving because nerves are moving and telling things to fire. So we've done these measurements. We've taken one of our sensors and we've positioned it on the hand to try and see, is there a way of measuring which fingers are firing in your hand at one time? So At the moment, the way this is done electrically is you insert probes. These are entirely painless. We stick little needles, like acupuncture needles, into the arm, and you measure changes in electric fields. It's still invasive, and so our idea is if we have one sensor which has vector sensitivity, can we figure out which fingers are firing? So these are some data that we have. If it fires your little finger, your ring finger, middle finger, and so on, and we can start to see correlations in this one, where if we put this into a closed loop optimization, we allow it means that we get a very high correlation measurement of which fingers are firing in the system. And this is for reasons about saying, is that I'm measuring here in the hand rather than in the fingers, so that if there is, for example, an amputee, you can measure the nerve signals that the brain is trying to send, and use this for robotics. And with this system, we can control a robot so that when I move my thumb, the robot moves his thumb as well. Whole bunch of work in this area that we've put into it, but the power of this came from using closed loop optimization or commercial off-the-shelf machine learning techniques. Right? So we've got our system here, which is, it's our system, it's complicated. We do some data analysis. We put this into the machine learning system, and it fully optimized our system. And so what this allowed us to do is to make our sensor precise enough in a very short amount of time so that it could measure these fields. And then it allows us to detect a signal much quicker. And so the end result of like 4 hours of optimization now means that our system works really well. And so the data we take out of it is that the way we did it beforehand, we actually have a 6-dimensional space, but we've narrowed it down to 3-dimensional space here. We went rastered across the system and found out where we would find the best performance. Then we tried these different techniques, this commercial off-the-shelf, free machine learning, some genetic algorithms, and gradient descent method. And we can find on here, this points on here, is that this is basically our cost function, which is our signal to noise ratio effectively, gets higher by using these, faster by using these very simple techniques. And our sensitivity now here, as I mentioned, that we can measure into the femtotesla. So now we're measuring about 200 femtotesla in this band from 10 to 100 hertz, which is exactly the frequency range that the human hand is moving. Okay, I'll finish up around this point just so that there's time for questions, and I can go back over anything if someone wanted to, or if I've said something too quickly. We've got a large team of people working together with a bunch of industrial and research council funding. But what I really wanted, maybe most important here, is just think of some take-home messages, is that magnetic fields are ubiquitous. It's everywhere, right? It's very, very difficult to get away from magnetic fields, and very expensive, as a matter of fact. The physics involved here is extremely simple. People first started thinking quantum mechanics, they found these things straight away. It is very much 1950s technology, but modern engineering allows us to do the new techniques that we're using. And by using these kind of modern engineering at low cost and scalable, allows us to go into interesting applications. And those interesting applications that I'm kind of thinking about are going to be because we can, sorry, my screens have moved around. We can make scalable systems. So what I was saying at the start is quantum technologies, is it that they're more accurate or more precise? We think we are more accurate and more precise in our systems. I think most importantly is that we made it a way that you can make lots of these different sensors. So if you were interested in detection of particular kind of sensors, particular kind of fields, and one example I'll show you here is someone asked a question, sorry, it's a slide I meant to include, is about drone detection. We've put these sensors onto drones, but it also allows us to detect drones as well. So the example on here is that this is a spectrum. So across the x-axis on here is time, and then y-axis is frequency. So each of these are individual slices. As we turn the drone on, we can see these changes in the frequencies of bands that we're measuring. And why these are different, why we're seeing these scaling upwards, well, what we're seeing on here is that this is the frequency the motor is running at, tens of hertz. And these are the gearing to cause things to go higher and higher frequencies. So this is the point that the drone gets turned on. We're seeing these particular signatures. This band all the way across here is 50 hertz, the Earth's ambient fields. The black here is because our sensitivity falls off. And then when the drone switches off, we get a spike, and we can see it disappear at that point. If we wanted to make lots of detectors of drones, I might want to make lots of these sensors. And if something is using glass-blown cells, that doesn't give me the confidence that I can make many of these and repair them at the time. So back to the point I was trying to make at the end, is the take-home messages is, with modern engineering, we can get interesting applications where we can do lots of these kind of effects. So at that point, I'll just say thank you for listening. And if anyone's any questions, more than happy to deal with those.
Yeah, thank you very much for your lectures.
Yeah. Oh, sorry. Yeah, thank you very much. So let's thank our speaker. Yeah. Questions? That's all from the local audience. Anton, do we have question online?
Yes, yes, we
Yeah,
do. We
because
do have
you know
several, and
we need some time to formulate.
so yeah, and I as well. I also have a lot of questions, but we start with online. So you mentioned atom trapping. I'm curious to know how atoms usually. Wait, sorry. I think this is the old. No, how would NV center magnetometry add benefits to these applications? Does it have something to do with sensitivity? You're muted. You're muted right now.
Not those feedback. Sorry. So for those who are not aware, NV centers are. So I'm saying we use atoms. There's lots of them. There's about whatever 120 different isotopes one has available out there. Sometimes you might want to think about making artificial atoms. So if I get diamond and you engineer a particular what's called a defect color center, if you introduce nitrogen into a diamond crystal, you can make it look like an artificial atom. And that artificial atom has magnetic sensitivity exact same as we said here. So NV centers have got different applications. One thing they really do is because it's in a hard crystal structure and can be made very small, these things can be made into very local probes. So if you are to make if you wanted to do an invasive measurement where you needed to measure it within the heart, and there are lots of applications where one would do that, is much easier to do rather than trying to introduce a cesium gas and other lasers. So nitrogen vacancy sensors typically do not have the same sensitivity, but they got better spatial resolution. So like any sensor, there's going to be a compromise between the performance. So there's a lot of interesting work in NV centers for magnetometry, for quantum memories and quantum communication and sources. But the sensitivity typically is lower, but there are other applications, for example, spatial resolution, where they win. Yeah. But the physics is exactly the same.
So yeah, thank you. My question would be concerning the distance of the measuring of magnetic fields. So as I understand, there is like you provide it with two different type of application. One is like medical, one where we have to put like a helmet to measure like pico Tesla changes in the magnetic field. And then you mentioned that it's possible to measure the drones. Like, what is the distance of measuring the drones? Is it the same principle in terms of like the changing of polarization of atoms, or it's a different system? So can you comment on this, please?
Yeah, so there are different ways one can use to measure. So we have about 4 different modalities that we use for measuring of these fields, but they're all using the same basic physics, which is that we're measuring the back action. The magnetic field affects the atoms affect the laser beam. So there's usually polarization is one way. The distance you measure over is due to the fact that we've got a kind of sensitivity. At the position of the atoms, I can measure a field that's of order of 1 picotesla. So if you've got a large field far away, I can measure that, or if you've got a small field up close, you can also measure that. And it's the scaling. So the magnetic fields, if it's a dipole field, the dipole interaction has got a 1 over distance to be cubed. And so this would be an application of if you're trying to measure something underground. If it's a large field, it can be deeper underground, kind of like Mike Linsky would have talked about with his kind of work. But the physical techniques are essentially the same.
So yeah, so currently with drones, so what's the distance right now?
The distance depends on the type of drone, I'm afraid. Again, like any good answer, it depends. It's not very large. And this is one of the concerns is about how to make this work over larger distances. And one of the things we look in is instead of measuring at low frequency, you start measuring at higher frequency. So what we call lock-in detection is try and find the frequency of these motors that are moving around. So I don't have a clear answer for you on this one.
Okay.
Anton, I have a question, if possible. Also, typical Ukrainian question now. What about physical sizes and weight of such magnetometers? I mean, is it possible to use it, for example, for drones and in order for dividing, for example, pupils or something like this, which is now really important for Ukraine?
Yeah, we absolutely. So this picture here is of a system on a drone. So we have.
Okay.
So the whole device itself is about with 2 components. There's the sensor part, which is the laser, the cell, and the detector. That is about 3 by 3, maybe 10 cubic centimeters in total. And the electronics package is about the size of a large mobile phone at this point.
Oh,
so
okay.
here, Yeah. So this.
And okay, sorry.
Yeah.
Yeah. How far away should be this drone from the ground in order to measure, for example, changes of magnetic field caused by some irons? You understand which kind of iron?
I can think of the kind of questions you're
Yeah,
imagining. Yeah.
yeah.
So you can do it in two different ways. And the problem comes into is you've got a noise level and your signal needs to poke out enough above it. So if we think of some parameter space, I need to be able to make the signature of the thing I'm trying to find be larger than the background. And one of the problems we have with the background is some of the background is due to the Earth's field, right? And the Earth's field is large, it's 50 microtesla. But the advantage of the Earth's field is that it varies very slowly. Because, like I was saying, we've got this dipole interaction. The Earth's dipole is huge, like it's thousands of kilometers across. So what we do instead is a gradiometric measurement. We use two devices in one. And so if I take two measurements like at this distance apart, they will both measure the same Earth's magnetic field. But this pipe or whatever piece of iron that we're trying to find or whatever it may be has got this 1 over r cubed, 1 over distance cubed term. We would measure a differential measurement as a result of that. So we take these two sensors, we measure the fields, we subtract them. That gets rid of the common signal and then allows us to amplify the differential signal, which would be the gradient. So in this system, we try and do an absolute measurement and then we try and do a difference measurement to get rid of the background.
Okay, thank you.
That gets scales down to how big is the signal and how big is the noise.
No, I mean how high this drone can be relative to the ground. So this meter or 2 meters or.
Again, so some of these measurements are taken at 100 meters and some are taken at about 1-2 meters off the ground. So the target we're aiming for is about tens of meters that we're looking for. As in, you don't want to, yeah.
But not centimeters, yeah, meters.
It's above my head height. Let's put it that way. It's safe.
Okay, I see. Thank you. Other questions? So it seems that we don't have other questions. So then, I believe we can thank our speaker again. It's an important, very important topic now for us.